Let's get into an overview of reciprocating engines. The basic components of reciprocating engines are shown to the right-hand side of this slide. You have the intake valve, and then you have an exhaust valve. So what happens is that the piston at a position called top dead center ends up pulling in. So but when the piston goes down to the bottom dead center position with the exhaust valve closed, the intake valve opens and air and fuel mixture go into the piston cylinder device. Then the piston goes back up to top dead center with both the intake valve and the exhaust valve closed, and there's an ignition. The ignition pushes down the piston again, and then when the piston comes back up, the intake valve is closed and the exhaust valve is open, rejecting the combustion gases and the air when after combustion occurs. So it's 4 strokes, 1, 2, 3, 4. Piston goes down, takes in air fuel mixture, goes back up, compresses it, ignites, goes back down and goes back up to reject the combustion gases, and then goes back down again to take in a fresh set of air fuel mixture. So again, top dead center, bottom dead center, stroke. The width of the diameter of the cylinder is called the bore. So again, this is just a continuation. The stroke, this should be stroke, is the distance between the top dead center, bottom dead center, and the bore is the diameter of the piston, or the diameter of the inner diameter of the cylinder. The intake valve is where the air fuel mixture is drawn into the cylinder, and the exhaust valve is where the combustion products are expelled from the cylinder. And then you have clearance volume. The clearance volume is the minimum volume formed in the cylinder when the piston is in top dead center position. So this would be the clearance volume. And the displacement volume, sorry, this would be the clearance volume up here. And then the displacement volume is this area, which is the volume displaced by the piston as it moves between top dead center and bottom dead center. Then there's the compression ratio. The compression ratio, R, is the ratio of the maximum volume formed in the cylinder to the minimum volume. So it would be the volume at bottom dead center divided by the volume at top dead center. So as you can tell on a PV diagram, as you go through the 4 processes, right, you form on a PV diagram a cycle, right, because a cycle is basically a series of processes that eventually returns to the initial state. So as a cycle occurs, the area enclosed by the cycle is called the net work. So if you remember, net work is the area underneath the curve. So it's the area entrapped inside of the cycle when after the cycle is completed on a PV diagram. Now, there's this thing called mean effective pressure. The mean effective pressure is a fictitious pressure that, if it acted on the piston during the entire power stroke, would produce the same amount of net work as that produced during the whole cycle. So basically what it means that if you were to go ahead and assume that the whole cycle, the whole engine cycle, can be simulated as one process at constant pressure, right? It would be that work net would equal P delta V, right? Again, it's basically replacing the whole engine cycle as one constant pressure workout process on a piston cylinder device, right? So if I were to assume a piston cylinder device and I were to have work out at constant pressure, if I were to take the delta V as the max minus the min volume, that pressure is called the mean effective pressure. The pressure that it would take to get the same equivalent work out of one process at constant pressure, to have that net work equal the net work produced by the entire engine cycle. That's what mean effective pressure is. Now we're going to go ahead and look at two different types of engine cycles. One is the spark ignition engine, right? It's the combustion of an air-fuel mixture is initiated by a spark. So that would be, for example, most engines found in engines in most cars. And then another one is compression ignition engines, which is where the air-fuel mixture is self-ignited as a result of compressing the mixture above its self-ignition temperature. That is called a diesel engine, right? That's an example. For example, it would be a diesel engine. Let's look at the first of the two cycles, which would be the spark ignition cycle. This is called an Otto cycle, OTTO. This is a four-stroke internal combustion engine, and an engine in which the piston executes 4 complete strokes within the cylinder and the crankshaft completes 2 revolutions for each thermodynamic cycle is a four-stroke engine. So below is a schematic of both the actual and idealized cycle. So this is actually what's going on. So let's look at a pressure versus volume diagram. We'll start with the piston in bottom dead center, right? It goes up to compress the air-fuel mixture with both the intake and the exhaust valve closed. Once it is in top dead center, there's a spark that ignites the air-fuel mixture, which pushes the piston back to bottom dead center. When it hits bottom dead center, the exhaust valve opens, and the gases, and then then the piston goes back up to top dead center and expels the exhaust gases. And at that point, from the top dead center, it goes back to bottom dead center with the intake valve open, taking in fresh air-fuel mixture. That would basically look like this following diagram, right? You would have this type of these type of processes going on during the four-process, or i.e. four-stroke engine. Expansion, compression, exhaust, intake. Between the volume at top dead center and the volume at bottom dead center. A little complicated to analyze. So instead, there's this idealized version on the bottom part of this slide that's going to be used to approximate an Otto cycle so that it is a little bit more feasible to analyze. So let's look at the 4 processes that make up the idealized cycle compared to the actual cycle. So again, process 1 here is the compression of the air-fuel mixture, right? So we have bottom dead center, and then the piston goes to top dead center to compress the air-fuel mixture. We're going to call that isentropic compression. So again, from process 1 to 2. Then, process from state 1 to state 2, I mean. And then, in the actual process, at top dead center, the air-fuel mixture is ignited, and then the pistons push down the bottom dead center. Instead, we're going to replace that with constant volume heat addition. So what's basically happening is that we're not having the air come in and out of the system, right? If you remember, the cold air standard assumptions assume that air is in the system at all times. Here, if you think about it, once the piston goes back up to expel the combustion gases and to take a new air-fuel mixture, air is constantly exiting and entering the system. So instead of having the air-fuel mixture ignited and the temperature going up, right, and pushing the piston down, and the pressure going up, pushing the piston down, we're going to have something called constant pressure heat addition. So replace the igniting process of the air-fuel mixture with just a constant volume heat addition process to the air. So that's process 2 to 3. Here we have the exhaust stroke, where the piston goes back up to top dead center, and at the same time expunging or exiting the hot exhaust gases, right? Because the exhaust gases is hot. Well, we're going to replace that process with process 3 to 4, which is isentropic expansion. And then process 4 to 1, instead of having the intake of the air-fuel mixture, what we're going to have is just constant volume heat rejection, right? So when you actually exhaust the gases and take an air-fuel mixture, you're basically making the temperature inside the piston cylinder assembly go down because the exhaust gas is hot and the air-fuel mixture is at um, outdoor um, at a lower temperature. So basically, we have now, for the simplification of the cycle, four processes, right? The analysis of the four-stroke engine can be simplified significantly if those air standard assumptions are used. So when you actually use the air standard assumptions on the Otto cycle, the resulting cycle is called the ideal Otto cycle, and that consists again of the four internally reversible processes. You have process 1 to 2, isentropic expansion, process 2 to 3, constant volume heat addition, process 3 to 4, isentropic expansion, and process 4 to 1, constant volume heat rejection. Now, how do you do a thermodynamic analysis on this? Well, the Otto cycle occurs in a closed system. If you notice the idealization, air is never actually leaving the piston cylinder device, right? The piston cylinder device is undergoing a cycle, four processes, and the air is never actually leaving. So to simplify, we're going to assume that the kinetic and potential energy changes will be disregarded. And so the energy balance can be basically, for any process, can be expressed in terms of per unit mass as the following. We get Qin, right? The Qin, if you were to do a first law analysis on the Qin process, which is constant volume, you would have it as delta U between the start and finish state of the process. And the same thing for Q out. Q in and Q out are both constant volume processes. So if you were to do an analysis of E in minus E out equals delta E system, for the Q in process, there's no E out, there's just Q in, and that has to equal the change in internal energy of the process. Same thing for the Q out process that's occurring at constant volume. You would have E in minus E out equals delta E system. There's no energy in, there's energy out by heat, equals the change in internal energy of the system. And then if you were to take this a step further, you can actually, using cold air standard assumptions, approximate the delta U as CV delta T. Remember, cold air standard assumptions assumes constant specific heats as part of the cold air standard assumptions assumes constant specific heats evaluated at room temperature. So again, that would be for the heat in process and heat out process. The thermal efficiency of the Otto cycle under the cold air standard assumptions becomes the following. So if you look at the thermal efficiency of a heat engine, that would be net work over Q in. Well, net work is Q in minus Q out. If you look at a total cycle, now the total first law analysis on the whole heat engine cycle, you would get that the net work produced would be the Q in minus Q out. That divided by Q in, so that reduces down to 1 minus Q out over Q in. Now I can replace Q in or Q out as CV delta T. I can replace Q in as CV delta T. And if you remember, according to cold air standard assumptions, CV is evaluated at room temperature. So since CVs are all evaluated at room temperature, I can go ahead and cancel them out, and I get my thermal efficiency as a function of temperature. Right? I can also get my thermal efficiency as a function of the compression ratio. Again, where the compression ratio is the max over the min volume. And also, how do you evaluate the temperatures? Well, if you look at process 3 to 4 and also process 1 to 2, they are isentropic, right? So we have here an isentropic process for an ideal gas with constant specific heats. So that means quantify T3 over T4 as equal to V nu 4 over nu 3 to the k minus 1, and also T2 over T1 as nu 2 over nu 1 to the k minus 1. And since nu 2 is equal to nu 3 and nu 4 is equal to nu 1, I can actually go ahead and equate T1 over T2 as equal to T4 over T3. Because if you remember, the compression ratio is nu 1 over nu 2, where nu 1 is equal to nu 4 and nu 2 is equal to nu 3. So you actually, if you go ahead and you combine again your previous, combining the previous equations with the efficiency equation we looked at earlier as a function of temperature, as I mentioned in the prior slide, you can also get the efficiency in terms of the compression ratio, again, where the compression ratio is the max volume over the min volume. If you go ahead and plot that, you can actually go ahead and see the efficiency of the Otto cycle as a function of the compression ratio. And you can see this area here represents the typical compression ratio for gasoline engines. And so that gives you sort of the maximum possible efficiencies that you can get from the Otto cycle for those compression ratio ranges. So as you can tell, the thermal efficiency increases with both compression ratio and also specific heat ratio. So again, the plot on the upper right shows the thermal efficiency as a function of the compression ratio. And in practice, when high compression ratios are used, sometimes you get premature ignition of the fuel called auto ignition. Auto ignition produces something called an inaudible noise called engine knock. So the efficiency in the Otto cycle can also be improved by using a working fluid with a high specific heat ratio, as shown in the bottom right-hand corner.